got this far into it. For a general change in state, system state 1, state 2, the change in free energy, gives free energy, gives the constraints of constant pressure and temperature, which are the ones that we are considering at the moment. Then we have this ubiquitous equation, which, because of this general relationship right here, we've cast the chemical potential of every species, every possible state into that form. So potential is equal to that in standard state plus RT log with activity. Spend some time deriving exact expression for systems in different states, both of aggregation and composition. All right, so we followed some steps. I haven't put them all in here, down to this expression that the change in free energy reaction is RT. We have to have this unit mole in there because we could not take the unit mole brackets up the exponent on law of activity. Just can't do that. It doesn't go, it has to stay. Nobody needs it there. But I try to leave it there. I keep forgetting sometimes because I was taught the way you all were taught. Even though that was a year or two ago, it still sort of sticks with you eventually. You can make these mistakes. So I'll try to see how I got it there so I extra it in. Anyhow, we have this relationship. Now, we are going to work some samples to see how to use that. And I just have a couple of pages that pre-written here so we can run through them. The easiest example to begin with probably is, as always, considering gases. And you can't have a reaction with just a pure gas very well, so you've got to have more than one species. So in general, we're looking at a homogeneous ideal gas phase reaction, constraints of constant pressure and temperature, and it's just a generic reaction, some reactants and products. The activity is always a ratio of gigacities. Gigacity is the pressure or partial pressure or vapor pressure, whatever. Every material has some equilibrium pressure. It's gas, it's gas pressure. It's a liquid, it's a vapor pressure. It's a solid, it's its vapor pressure. And it may be unimaginably low, but it's there just the same. And gigacity is a pressure that is corrected for non-ideality by the equation that we put on ahead in the last lecture notes. The activity is a ratio of gigacities. Gigacity in the state I, state whatever the system's in, divided by the gigacity in standard state. For ideal gases, the gigacity is just the partial pressure. And the partial pressure is just the mole fraction times the total pressure. And so for ideal gases, we have this relationship here for the activity. Our curly cube, which is this product of activities raised to the appropriate, these are just the numerical values of the numbers of moles in the balance equation. Just pure numbers there. And it would look something like this for ideal gases. And K, of course, is the value of this ratio of activities when the system's in equilibrium. So that's a general homogeneous gas phase reaction. Here's a specific one. And it's a real easy one. But we can use that to illustrate most of the important points I wish to make. And all I really have time for is just to show you some of the highlights. So, iodine. Have you ever seen elemental iodine in a bottle or somewhere? If you do, what do you notice? Anybody ever seen elemental iodine? Yeah, what do you notice about it?
Solid.
It's a solid, but in the space above it, you ever see any?
It's like purple.
Yeah, there's a vapor in it. It's volatile. beautiful purple vapor. And it's not very intense at ordinary temperatures because the vapor pressure is low. So I'm talking about iodine now as an ideal gas, and dissociating into atomic iodine. This is a real simple concept, a real simple reaction. We don't expect this to happen much at room temperature, but we can talk about it just a second. So this is our reaction. Now when I work problems like this, I usually gather up the data that's available, such as the standard molar enthalpies, and I go to the table in the back of your textbook and look these numbers up. And the chemical potential, they're not listed as chemical potentials though, they're listed as free energies, but the chemical potential is the partial molar free energy. I looked them up. I put in the heat capacity here because we'll need that when we try to find out what this free energy is and what its equivalent constant is at different temperatures. You don't always want to work at 25 Celsius. You want to be able to deal with reactions at other temperatures and pressures. So I put that in. This is the tabulated heat capacities. It's interesting, I would think, to all of us, should be, that the monatomic species iodine, atomic iodine, that its heat capacity is 5 halves-hours. Is that a surprise? Shouldn't be, because that's exactly what the kinetic electric theory predicts and the partition theory predicts for a monatomic gas. And it is, that's what it is. We'll look it up. Boom. Now here we have a diatomic gas, and it has 3 degrees of translational freedom, so that gives us 3 halves R for translation. It has 2 rotational degrees of freedom, gives us 2 halves R for rotation. It has another R to change heat capacity constant volume, heat capacity constant pressure, and then it has some contribution from its vibration. Now we found for nitrogen and hydrogen and molecules like that, the vibrational contribution is negligible at ordinary temperature, just zilch. But how about iodine? What do you got? Great big old massive heavy atoms on a little wussy spring, and it doesn't take much to shake that. And this means that the spacings between the vibrational energy levels is low. And it's low of the magnitude of KT at 25 degrees Celsius. So KTs are big enough, when they bump into one, they're big enough to change their vibrational energies. So there's some vibrational excitation in iron. If it were fully excited, it would be If we're fully excited, the I2 molecule would be 9 halves R, or 4.5 R, and it's 4.4, so you see it's getting close at 25. I mentioned this because we're going to heat this up in a minute, and I'm just going to assume it's already gotten up to that big tissue. Now, just to make our calculations easier, if you're a chemical engineer and you're trying to make a living at this, and you've got to put in all those details and integrate over these changes. All right, so from these data, then we can write down delta H 0 for the reaction. And the thing I would emphasize about it here is that it's positive that the reaction is endothermic. Every dissociation. If you see a reaction where you've got a molecule and it's broken into its parts, then that's endothermic. Otherwise, it wouldn't have a molecule. We'll make something out of that shortly. Delta G0, just play the same game with the chemical potentials here. And it's positive, and I indicate it's greater than 0. And that tells us what? That tells us that there's not a big driving force for dissociating I2 molecules when the temperature is 25 degrees Celsius, right? We don't expect that. And when you looked at the vapor, you didn't see atomic, the iodine atoms wouldn't have any visible color. You see the purplish, because that's the molecules that are absorbing light and giving that appearance. CP is 0.56 R. At equal position, if it were fully excited, delta CP would be 1/2 0.5 R. We'll make that assumption in a bit. So, I'll check it down here. So we're going to see what delta G0 at 298 Kelvin, or what I might call delta G0 at T0 is. And we wrote that out a moment ago, and it was equal to, I think, 121.17 kilojoules. But it's also equal to minus RT, and I have to write mole in here, logarithm of K. And this is K at 298. We want to know what K is. K is equal to E to the minus delta G0 over RT mole, and that is equal to E to the is it not a minus sign there? All right, it's equal to E to the minus 121.17 joules over R 8.3144 joules per K per mole, and temperature is 298.15 K, and mole is mole. Now look, some of you lost points because you don't do this stuff very much. That's all right. No one's twisting your arm, but you didn't want to bleed in joules, and you don't have to. And you didn't want to bleed in kelvins or inverse kelvins, and you don't have it. And what's left over here? Well, if that's not there, you got an inverse mole. And that exponent, and that ain't, something's got to get rid of that. What is it? It's that one that was there all along. It's there. And I tell you folks, if you don't do that, you're not doing science. You're just doing, you're just mimicking. You're just reciting a mantra, you're reciting a catechism, you're just going through the motions. I'm not telling you that that unit's important to science. It's just that you should use an equal sign if what's on the website is not equal to what's on your website. Okay, well, so we do this, we get E to the minus of 48, about 48.9, and that's pretty close to zero. That's pretty close to zero. And that says that there's no significant dissociation of high-2 gas at 298 Kelvin or 25 degrees Celsius. So how do you force that? I like this reaction to be a reasonable reaction we talk about. How do you force it?
Heat?
Yeah, you heat it up. Exactly. It's an endothermic reaction. You raise the temperature. That you learned back in high school. You know what the principle of Chatelier, or whatever you call it. Thermodynamics has that built in. You don't have to have a separate rule for it. But you have an endothermic process. You raise the temperature. You drive the reaction over to the product side. So if we want to get something that is far removed from zero here, we need to raise the temperature. So how to force dissociation? Well, one way is to raise the temperature because the reaction is endothermic. So that means we need to ask the question, what are delta G0, T, and KT at different T than 298 Kelvin or T0? ways to do this, and I have time just to tell you about one. I'll tell you the most practical one, I think. We need either values of the partial derivative of delta G0 with respect to temperature at constant pressure, or the partial derivative of the equilibrium constant with respect to temperature at constant pressure, or some other related partial derivatives. And there are a couple of them. So we're going to consider the definition of Gibbs free energy. G is H minus Ts. And we're going to play some games with this. We're going to divide both sides by T, we get H over T minus S. And we are going to differentiate with respect to temperature at constant pressure. So we have the derivative of G over T with respect to temperature at constant pressure is equal to, all right, now we're going to differentiate this right-hand side. Well, the way I learned that 100 years ago was that you write the denominator times the derivative of the numerator, that's the partial H, with respect to temperature at constant pressure, minus the numerator times the denominator, that's 1. Divided by the denominator square, that's T squared. Right. And then we have minus the partial S with respect to temperature at constant pressure. Right. Well, by now, this little bugger here should look like something to you. What is that partial derivative there? Partial H with respect to temperature at constant pressure. That's got it there.
Isn't that heat capacity at constant
It
pressure?
is. It is. It always is. Every time you see that derivative, it's heat capacity at constant pressure. All right. So this is T times the heat capacity at constant pressure, and this is minus H, and this is divided by T squared, and this is minus, oh, now what's ds? ds is dq reversible divided by temperature, dq constant pressure. Oh, let's play some games with this. All right, take these two terms. I have the capacity over temperature, I have minus enthalpy over temperature squared. I have minus, 1 over T, I take that out. Now, what's left over is a partial of Q with respect to T at constant pressure. What's that? What is it?
Is that?
What is what? That's a partial, partial Q with respect to temperature at constant pressure. What's the name? Heat flows to something, raises its temperature. The ratio of the heat flow to temperature change is called
Entropy?
Yes, huh?
Is it the entropy? No.
It's the bleeding heat capacity.
Oh.
It's the same damn thing. It's the heat capacity at constant pressure. So it's heat capacity constant pressure minus H over T squared minus heat capacity constant pressure divided by T. Those cancel out. That's what's left over. Now, there's a lot of steps to go through to get that little equation. So we're going to use it. So I'll write the partial derivative of G over T with respect to temperature, constant pressure is equal to minus H over T squared. Well, what if I started with, instead of G is equal to H minus Ts, what I'll start with delta G is equal to H minus Ts. H minus T times delta S. This is T as a constant. What would I do? then I've got partial of delta G over T, space temperature, constant pressure is equal to minus delta H over T squared, right? I'll get like that. What would have happened if I'd started with G0 is H0 minus TS is 0? I would be put the opposite. Now, I would have gotten the partial of delta G to 0 over T, respect to T, constant pressure is equal to minus delta H0 over T squared. And that's the one we want, because now we say that the derivative of delta T0 over T, delta T0, yes, at whatever temperature it is over T, is equal to minus delta H, delta H is 0 over T squared times dt, and we integrate this, we get delta G0 T over T minus delta G0 T to 0 over T to 0 is equal to minus the integral of delta H0 over T squared dt. And that's the way we want to find what the standard free energy is at some other thing. Well, you have to know the heat capacity. You have to know the standard heat of reaction. We got that tabulated. We tabulated that right away. We calculated that per se of this reaction. You got to know the heat capacity. Well, we talked about that already as well. So this is the equation. Will let us find the standard delta gives free energy at any temperature, starting from the tabulated value. Okay, this is the one that they tabulate. This is the one you plug somewhere else. This is delta H is a function of temperature. Recall, hate to say this, you have to remember some things that are done before. That's basic. We recall that delta H at temperature T is related to delta H at T0 plus the integral of what? Delta Cp dt. So we do this, we can put zeros on here if we want. Add, so if I put a 0 on there, I get delta H 0 T 0 plus R. For R, well, it's plus this delta Cp 0 T. For I2 gas, going to I gas minus delta dt, we have delta Cp was approximately 1/2 mole times R. And it was very close to that at 298. 4.44, I mean, it was 0.56, so it was 0.56. And as you raise the temperature, it gets closer to 1/2. So we're just going to say, let's assume that delta Cp for this reaction is 1/2 mole times R. Then delta G0, some other temperature, is equal to delta G0 at 298 Kelvin, the one that we this is not a function of temperature, so we could write plus 1/2 mole R times the integral T0 to T of dt. So just softly say again, take that. I'll just say that, whoa, don't let me do this. Don't let me do this. I'm ahead of myself here. Delta H 0 T is equal to delta H 0 T0 plus delta CP times T minus T0. I can probably just put it like that. Now that goes into that previous equation. Right here. And you can see that's a bit tedious. We get that delta G, now I'm doing this correct, delta G 0 at some temperature T divided by T minus delta G 0 at standard temperature T0 divided by that temperature T0 is equal to minus the integral of delta H over T squared. And delta H is this mess here. It's delta H 0 T 0 plus, now we're at minus delta CP T 0. And then it is plus delta CP T all divided by T squared times dt. And this is constant here. So you got 2 times. We integrate this from T0 to T. So that if T is 1500 Kelvin, that delta G0 at 1500 Kelvin is equal to minus 5.23. Now, you said, well, that's going to be a lot of work. I can do that for you. I've got it written out here. 3 pages together. I'm going to put them in the notes so you can see it. But you do it yourself too. And see if I'm not. I may be wrong. So just skip ahead. We'll assume that's the right answer. If that's the right answer, notice that this is now less than 0. And that implies what? That there's a driving force for spontaneity in this direction. Isn't that what it is? Constant pressure temperature, delta G is negative, driving force for spontaneous change. That means we're going to have some dissociation. This is also minus RT mole times the logarithm of K at 1500 Kelvin. And so we solve K at 1500 Kelvin. That's E minus delta G over RT mole. And that's E to the plus 5230 joules divided by 8.3144 joules per K per mole. Times T is now 1500 Kelvin, and mole is still mole, and they're all there, and all cancel out again. And you get E to the 0.42, and that turns out to be about 1.52. That's not a very big equilibrium because it's not kind of like everything's 0. So where do we go from here? Remember we set out to show that 25 degrees Celsius or 298 Kelvin, that there essentially was no discernible dissociation. We raise the temperature up to 1500 Kelvin, and there is some association. How much? So, what is the equilibrium composition of iodine vapor at 1500 Kelvin and some pressure? That's our next question. Find the equilibrium composition of between I2, the iodine and its associated form. At some pressure T, temperature T. Okay? So we're going to say at P and 1500 Kelvin for now. So this is another calculation. You have to be good doing these calculations. You may get a chance to try this. I don't know, but it's good. You've all done these things before, I'm pretty sure. So let's write that equation down. I2 S 2I S. And we're at the well, you have to sort of imagine we got a reactor here to put in some I2, and we get an equilibrium here between that. So I want to know what's the mole fraction of I2, what's the mole fraction of I, what's the ratio of them, what's the composition. This is at some temperature, this is at 1500. So suppose we just put the iodine in at some time starting, and we have 1 mole and none. Then total number of moles is 1 moles of gas. Now, how long does it take to reach equilibrium? It's equilibrium state we want to talk about next. Who the hell knows? We talk about that when we do reaction next, soon to finish this stuff. But sooner or later, it'll be equilibrium. So when I don't know, I just say that's long enough. It'll get to equilibrium at that temperature. And then we will have how many moles of this? B1 diminished by some amount, which I just call alpha, for want of a better term. And how many moles of the monatomic item will we have in there?
2 alpha.
Thank you. And what will the total number of moles be?
1 plus alpha.
Thank you. Excellent. And what will the mole fraction of I be at equilibrium? Well, what will it for I2? Be 1 minus alpha over 1 plus alpha. Right? What will the mole fraction of the monatomic species be? 2 alpha over 1 plus alpha. Everybody see that? What will be the sum of the mole fractions? It'll be 1. What will the partial pressure of these species be? Well, it will be the mole fraction of I2 times the total pressure, whatever it is. It will be the mole fraction of atomic iodine times the total pressure, whatever that is. What will be the sum of the partial pressures? It'll be the pressure. What will be the activity of these species at equilibrium? the I was in equilibrium to? What would be the activity? Whoa.
You'd have to do the fugacity
Say it
first.
again?
You'd have to do the fugacity first?
Yeah, but these are ideal gases.
Oh, okay,
And
so,
the gas in an ideal gas is its pressure, partial pressure. So other,
it'll be, wouldn't it just be the partial pressure?
well, activity of I is Ti over T0.
Yeah.
And so it would be X I2 times T over T0. This would be X I times T over T0. T0 is 1 atmosphere. So what would the equilibrium constant be? K is equal to curly Q at equilibrium is equal to, for this reaction, equal to activity of I squared over activity of I2 at equilibrium. Now notice, equilibrium constants are always dimensionless. I know you learn about Kp, K this and K that, K the other, but thermodynamic equilibrium constants are dimensionless. Why? They're ratios of activities, and activity is dimensionless. It's a ratio of your gases. Always dimensionless. So that's what it is. At equilibrium. Well, hell, we know what this is. Now, it is equal to X I times P over P0 squared over X I2 times P over P0. And I can write that K times multiply P0 over P is just equal to X I squared over X I2 at equilibrium. Wow. Now we know K, and we know P0. This is at 1500 Kelvin, obviously. That's the one we're calculating for. So we can calculate with more practice. Matter of fact, this is equal to what? This is equal to 2 alpha over 1 plus alpha squared over 1 minus alpha over 1 plus alpha. And that's not too hard to fiddle around with those a little bit and see that K at some temperature T, it'll be 1500. It is 1500. E0 over P is equal to 4 alpha squared over 1 plus alpha times 1 minus alpha. And that is equal to 4 alpha squared over 1 minus alpha squared. And solve for alpha squared, and you find alpha squared is equal to K times P0 over P over 4 plus K times P0 over P. And you'll find that alpha is equal to K times P0 over P over 4 plus K times P0 over P to the 1/2 power. Okay. K at 1500 was equal to 1.52. At P is equal to 1 atmosphere. T0, we have alpha at 1 atmosphere and 50 K is equal to, it's 1.52 over 4 plus 1.52 to the 1/2 power, and that is equal to 0.525. Now, is that a lot to ask students to do on the test? Yeah, it probably is. But is that hard? It's not hard, it's just Jesus. So what does that mean? Well, we have to go back and look at, what these partial pressures were. Where that was, that's way back there somewhere. Go back, look at partial pressure quick. Partial pressure of, I2 is, here we go. Here's our alpha. Okay, alpha is how much of the I2 is associated, right? That's what it is. How much is associated. So this means that how much is associated. I2 gas is 52.5% dissociated. That's what atmosphere at 1500 K. So that's cancer. That's physical cancer. He did it. It's not necessarily fun, but that's what you do with these things. Now I ask you a question. What happens to this dissociation and change of pressure? It's all right to have gut feelings, even in class, mixed sexes that have gut feelings. So, what do you think? We keep the temperature still 1500 K, we just change the pressure. Press it. Squeeze the gas down. That make the dissociation get bigger or less? Now, Brian says to go down. I agree with that. Squeeze it together, and you're going to force reaction back the other direction. So I just say show that at 1500 K and 2 atmospheres, the percent dissociation is about 40% less, just like Bryce showed. Now that would be easy to put on the test. See, if we had this silly equation here, all you gotta do is go in and instead of letting P be P0 at 1, you now let it be I. Okay, that's enough. Not all reactions that chemists, engineers often look at are homogeneous gas phase reactions. Some are homogeneous liquid phase reactions, many of them are, and some are heterogeneous reactions. Let's look at a real simple heterogeneous reaction, just to learn some of these rules. So, before I do this, let me back up and say, now notice on that last reaction we talked about, we saw how to start at standard conditions, 1 atmosphere, 25 degrees Celsius, and move the temperature, and move the pressure, and all the fundamentals. There's a lot to that, a lot of potential to that, not much of that big calculation. Or will it be this one? This is a very simple one. It's going to be water in the liquid phase. And that's our only reactant. Well, what the hell can it do? Well, we could associate it too, but I'm not going to do that. And you really got to get that hot to associate it to its atoms. So we're just going to let it go to vapor phase, gas phase, minus delta G at T. We'll just do it P0 and T0 for now. I look at U0 for water, and it is minus 237.13 kilojoules per mole. that's the number that's supposed to be on that test last Friday that you're supposed to get, or that I mean, this is the number we calculated, it should have been on that test. And by dyslexia, I don't know, I was never dyslexic as a child or even as a man. And now I'm old too, getting bad about it, turn things around all the time, especially when I'm putting things on the keyboard. So I typed that in as 273, 113. And so you get the wrong answer with the calculator, but that's the right answer for the test, because that's the data I gave you, and I apologize for that. Now for the gas phase, it is, and these are right out of your textbook, minus 228.57 kilojoules per mole. And delta G, 0 is just equal to the summation of UI 0, and that is just equal to 1 mole times minus 228.57 kilojoules per mole plus 237.13 kilojoules per mole, and it is equal to plus 8.56 kilojoules. And this says that the driving force of responsibility is for water vapor condensed. Wilson. All right. So delta G 0 is equal to minus RT mole logum of K. And K is equal to E minus delta G 0 over RT mole. And you put the numbers in. Put the mole in, everything cancel out, and you'll get E to the E minus, I put a lot of figures in here because this, we know a lot about water and a high degree of significance, so I just included all the ones that I could find, 4, 5, and 1. And that turns out to be about 0.03169, something like that. That's the equilibrium constant. But the equilibrium constant, K, is equal to what? It's equal to activity of water vapor over activity of water liquid at equilibrium. And the activity of the vapor, we'll treat it as an ideal gas. It'll just be, it's a solid, you gas the standard state. But for an ideal gas, the gas is a pressure. And we know water vapor has a low pressure, so it's probably pretty close to ideal. So we'll say this is the stochastic of the vapor. Oh, stochastic 0. What's the activity of liquid water?
What's that?
What is the activity of liquid water? Who said that? Yes. You say it's 1? You're absolutely right. It's 1. It's not approximately 1. It's not almost 1 or near 1. It's 1. Because that's its standard state. Liquid water at this temperature pressure is its standard state. It's active with water. That's an easy one. So this is just the pressure of the vapor over 1 atmosphere over 1. So the pressure of the vapor is equal to K atmospheres, and that's 1031649 atmospheres, and multiply that by 764, you turn it in per atmosphere, you turn it into torr, and it's 24.454. Now, you have fond memories of your days in freshman chemistry laboratory where you must have collected some gas over water and determine how many moles you had. In order to do that, you had to subtract off the pressure of water and the gas. And you must have done that. Didn't do that, and you missed out on the real fun, special chemistry. And how do you find the vapor pressure of water in those days? Did you go back to back, you look at the little table of vapor pressure of water temperatures, and you find 25 degrees or whatever, just a few floor and use that? I'm hoping you had that experience. If you didn't, you were cheating. If you go back in the pressure temperature book and look back, you'll find a table of vapor pressures of water. And if you find one at 25 Celsius, I want to be that. Where'd that come from? You measure the light for it, so you calculate from the light. Now, if you go into the textbook and look, you'll find standard chemical potential for all sorts of vapors, exotic vapors. You find it for maybe carbon vapor, tungsten vapor, aluminum vapor. Why? Because we can calculate those from statistical mechanics. We can calculate them more accurately than their measure. And it's sort of fun to do that and find out that you have the number of tungsten atoms in the vapor phase at 25 degrees Celsius that would fill a sphere the size of the solar system, you know, about water too. So, some of that's just crazy stuff. All right, does that make any sense? Now, we know the devaporization of water. We saw that earlier. It's about 44.0 kilojoules per mole. So, what's the effect of temperature on vapor pressure of water? Well, if you raise the temperature, you're going to raise the vapor pressure. You know that. And we can calculate that with delta H and heat capacity. We can play the same game we did for the dissociation of iodine. Calculate delta G to 0 at, say, 10 degree increase at 298 would be about 308 Kelvin. And K at 308 for our dissociation reaction. And heat vapor at 308 Kelvin. That should be able to show that it's around 42 floors. Okay. But we have another way to do this. Or call the Clapeyron equation, which essentially assured us that the equation or Clausen-Clapeyron equation, which is approximate, and it went at P of the vapor, or P0 is e to the minus delta H vaporization over R times 1 over plus 1 over P0 minus 1 over P minus P wave. So you calculate it that way. Either way, you get that same result. do you use the data for simple systems like gases, especially ideal gases, and pure condensed phases like water? We have to add some things too when our reactions involve solutions. Condensed solutions, not just gas solutions. So we've got to go back and revisit and expand on what we have said about the solution chemistry in the past. Place it again, as usual, is with a certain class of solutions. What would that be? Well, it would be a class we call ideal solutions. We talk about gases, we start with ideal gases, then we talk about departures from ideality, we talk about condensed solutions, we talk about ideal solutions, and then departures from ideality. Sort of a natural sequence of events. And we've already done, I laid the background to this pretty carefully some time ago, and now I'm just about fingers crossed that you will remember it, because I can't teach it all over again. I was asked, when I introduced the idea of harsh molar quantities, I said they're going to be important, especially in thermodynamics. So you can see that fact has come to pass. And introduced that with volumes. Volume of extensive state variable, and we looked at the volumes of mixtures and compared them to the volumes of the pure things of which the mixtures were made. And we found they didn't always add up the way we expected. Sometimes the volume of the mixture was greater than that of its parts, sometimes it was less than that of its parts. And when it was greater or less, those solutions were not ideal. When it was the same, they were ideal. And what was the effect that determined ideality or departure by ideality there? It was we got molecules in a pure liquid all the same. And what holds them in the liquid is the affinity between them. These cohesive forces that we talked about in the past. And the tendency to evaporate up here and form a vapor at a given temperature is a measure of the temperature, the kinetic energy, and the strength of that measure. If the molecules cling together real tightly, the vapor pressure will be what?
Small.
If the molecules are loosey-goosey at that temperature, then the vapor pressure will be high. If we have another pure substance, different kind of molecules, we'll have the same arguments. Now, the thing that determines the vapor pressure is the affinity between these molecules. But if we make a mixture of them, then here we have all this species 1, this species 2. We have the cohesive forces between molecules 1 interacting with one another over here. Cohesive forces of 2 2s. And in here we have what? We have some 1 1s, we have some 1 2s, we have some 2 2s. And if these differ from those others, that solution is not ideal. If the molecule doesn't discern much difference when it goes into a solution with forms, then it behaves much as it did when it was with its own. If it likes them better and they cuddle up closer together, then it's bound to them more tightly. And they hate each other's guts and try to get away from one another, they're bound together less tight. And what effect that have on vapor pressures? Well, that will either reduce the vapor pressure or enhance the vapor pressure of what we might anticipate in the system ideal. So this is a little reminder of where we were with that. Here's the story for Ideal Solutions. This is the thermodynamic results here will include all ideal mixtures, whether they be gases, liquids, or solids. Ideal solutions. Here's some molecular pairs that form very nearly ideal solutions when you mix it together. Benzene and toluene. Is that a surprise? No, not much. It's pretty simple. They're not identical. They're identical to the same molecule, but they're pretty simple. What would you think if I had benzene and I'll add that? Can you make an ideal pair? I don't think so. Here we have non-polar molecules, and here we got a big old dipole on one, and that's going to partner things up. So forces are going to be different between the dissimilar molecules. So this is non-ideal. So why don't we add this one? Turns out that forms a very ideal solution. Not perfect, but with a good facsimile. How about this? Carbon tetrachloride and silicon tetrachloride. These are all near ideal solutions. That would be not ideal. Now, if we just barely have time to make this drawing. If I picked any one of these pairs and plotted the mole fraction of one of the species, 0 to 1, or the mole fraction of the other species goes from 1 to 0, and we got vapor pressure over here. And so one of them has a P, this is P2 0, and another one has P1 0. There's vapor pressures. What would be the vapor pressure of solutions out here at different compositions? They would follow this straight line. What would be the partial pressures of the species? They would follow these straight lines. That's the behavior of an ideal solution. So that the B1 is equal to X1, B1 0, and B2 is X2, B2 0. And the total pressures are sum of those. That's that line there. These are the equations. So I have three straight lines, I have three equations here. And this defines the behavior of ideal solutions thermodynamically. So tomorrow,